Hi everyone, my name is Ruben Wiersma, here to talk about uncertainty for SVBRDF acquisition. So we want to capture digital objects from the real world, to use as digital doubles in AR, VR games and movies, or to digitize cultural heritage objects for virtual preservation. Now, in recent years, multi-view capture has made this very simple. We just take a couple photographs and the camera positions, and that allows us to reconstruct high-quality geometry and novel view synthesis. Now, we also want to know how the light interacts with the objects and model this, because we want to make sure that the objects interact naturally with their environment. So for this, we need to fit some model of how light interacts, some spatially varying BRDF. And a pipeline has emerged over recent years to reconstruct this, both geometry and materials. We take a couple of photographs, and we have a model of the geometry and the material and lighting. This geometry is differentiable in the materials as well. We render these through a differentiable renderer, compute a loss function, and then update the geometry and material through the gradients from this loss. This approach already gives very impressive results, but we felt an important question was underexposed. What is the limit that we can achieve by improving only the models and algorithms? In other words, when have we squeezed all the signal out of our data? Now, because we only use a couple of photographs and fixed lighting, there might be some regions where we're missing information. Now, let's illustrate that with a simple example. Which of these planes is more matte, and which one is more like a mirror? Now, how about these planes? Now, what if I told you that these are both the same materials in the different scenes, but the combination of the viewpoint and lighting makes us uncertain in the left case and certain in the right? Now, to illustrate the solution that we'll eventually come up with, let's take a look at the frequency of the signal that we see. On the left, both our planes have low frequency information, almost a constant function. And that's because our input lighting is also low frequency. In the right, we can see that the mirror-like has higher frequency details, and these show up because we have high frequency lighting. So in our paper, we quantify this uncertainty, and we do this with entropy. Now, entropy measures the spread of a distribution. In this case, our distribution is uniform. Both matte and mirror are equally likely. And in the uniform setting, entropy is maximum. So maximum uncertainty, maximum entropy. In the blue sky example, where we have high frequency detail, we have only one material that is highly likely. So we have a concentrated probability distribution and therefore low entropy. Now in practice, it's not that easy because we have more parameters in our models and they typically are continuous. Moreover, if we want to evaluate this probability distribution, we have to render our scene from all the input views. Even if we discretize our parameter space coarsely, so 8 by 8 by 8, that already takes 6 minutes with a path tracer. And we want to be real time to be able to guide our camera placement or to do repeated computations. If we want to go higher resolution, like 16 by 16 by 16, it already takes 50 minutes. So we need to do something faster and maybe approximate. And that's what other people already do. So they approximate entropy, for example, by saying the probability distribution resembles a Gaussian centered around the optimum with the covariance matrix equal to the inverse of the Hessian of the reconstruction loss. This is called Laplace's approximation and already used by Lench and colleagues in 2003 and in the context of NERF by Goley and colleagues in 2024. Downside of this is that it's after optimization and only a local approximation, which doesn't always fit the real probability distribution. Another recent approach by Zhou and colleagues optimizes samples using particle optimization and then take the variance of these particles in parameter space as uncertainty. Now this still takes quite a long time and is orthogonal to what we propose to do. In our paper, we propose to approximate the BRDF evaluation. We do this in the frequency domain. Now this is following a model developed by Ramamurthy and Hanrahan, who observed that the scattering of light from a surface can be approximated as a convolution of the BRDF with the incoming light. Now here's the intuition. Say you have a light source, and the light rays hitting the mirror-like surface into the angle of reflection. Now in reality, we often don't have perfectly mirror-like surfaces, but rough surfaces, and we model them as microfacet surfaces. Here, each ray hits a different microfacet and is sent into a different direction. But if we plot these rays, these directions, over the outgoing angles, we see that they follow a certain distribution. And as we move the incoming light source position, the distribution itself also shifts, similar to how a kernel shifts over the input image in a convolution. Now, a keen observer would note that not only the distribution shifts, but it also changes shape in reality. Now, we ignore this in practice because it allows us to approximate this BRDF evaluation as a rotational convolution. Let's look at images, why this matters. So for images, if we want to compute a convolution, we transform the signal to the Fourier domain, and in the Fourier domain, convolution is only a multiplication. We do the inverse transform with a fast Fourier transform, and that allows us to really quickly evaluate convolutions. Now for our spherical signals and with a rotation convolution, we can do the same for BRDFs. Now transforming to the spherical harmonics domain, computing convolution as a multiplication, and then doing inverse spherical harmonics transform to go back to the angular domain. Ramamurthy and Hanrahan use this to study the well-posedness of inversion, but they do not quantify uncertainty. So we take the following two steps. First, we use a spherical harmonics model within the context of entropy to compute the BRDF. This allows us to accelerate our BRDF computation and the ensuing entropy computation from 6 minutes to only 1.5 seconds. Now, it's good to note here that this model really is an approximation. In the original paper, they approximate the BRDF kernel, they approximate the Fresnel effect, and ignore shadowing and masking. In our paper, we show how you can still include this shadowing and masking with an approximation in the appendix. Second, we show that you can compute entropy completely within the frequency domain, and within the frequency domain using only the power spectrum. Now, this is really helpful because it means that we don't have to repeatedly transform from and back to the angular domain, but we can stay within the frequency domain. We can also parallelize the computation over our parameter space, and that allows us to compute this entropy from 1.5 seconds now in 0.5 millisecond, so 3,000 times speed up. And because we can parallelize, we can also do higher discretizations, higher resolution discretizations of our probability distribution. Now, to make both steps possible, we need to have some estimate of spherical harmonics transform. And we need to do this on sparse and irregular positions, because our camera positions, when we took our photographs, they're placed manually. In our paper, we show how to do this using a least squares approach with a specialized regularizer. Now, this can be computed analytically and in parallel. Now, for our validation, we wanted to make sure that our approximations are valid proxies for entropy. And as a baseline, we use Mitsuba, both for inverse rendering and for entropy computation. Now, this is a baseline created for the purpose of our experiments and not used in prior work. We use the Stanford Orb as a benchmark dataset, and it includes high-quality geometry and environment maps, so we can really focus on the materials. And in each of these scenes, we compute entropy using both Mitsuba and our spherical harmonics models. We find here that we have high correlation with the entropy computed with Mitsuba for a really high speedup, so almost 700,000 times speedup. We also show that the spherical harmonics model is still relevant for inverse rendering. On the Stanford Orb benchmark, it matched the state-of-the-art reconstruction in only a fraction of the time. In our paper, we have more validations and results. We test on a synthetic benchmark and include analysis of the relationship between entropy and error. Finally, we also show how uncertainty can be used in practice. First, by sharing information. For this shoe example, there are some erroneous regions on the side of the shoe and inside, but we don't really know where this error shows up beforehand. Luckily, we can use entropy. We take the most certain points and share information from these certain points to uncertain regions, using a match between the probability distributions. That means we compute KL divergence between these distributions, and that incorporates the uncertainty that we have about the materials. Second, we can guide camera placement. As a baseline, we place cameras at evenly spaced positions, and we compare this with a proposed method where we place our cameras in the places where we expect the lowest entropy. Using the selection mechanism, we can now sample camera positions that get to 1 decibel of peak signal to noise ratio gain for about 60% of the views. Third, we can use entropy as a mask to in-paint regions with a diffusion model. We use the RGB2X model to in-paint albedo, and we see that we improve regions where previously the method didn't work well. So things like shadow, and we fix this with the diffusion model. Using only diffusion model doesn't work as well because we don't have the lighting information and physical information we have in our rendering models. Finally, as a nice bonus, we show that you can use this fast estimate using the spherical harmonics model to initialize Mitsuba for a better estimate, also at a fraction of the time. So concluding, uncertainty helps us understand the limitations of our data that we can then fix using uncertainty. We compute uncertainty as entropy and approximate this within the frequency domain. In future work, we can make the model more robust, for example, working with low dynamic range lighting and unknown lighting. We would like to work with other approximations of the BRDF model, for example, to support more complex material models. And we want to see if there's a better way to sample this probability distribution space, so not with grid sampling, but maybe a Monte Carlo method. With that, I want to thank you for your attention, and you can find the paper, supplementary, and code on our project page.